So hello, good morning or good afternoon or good night, depending where you are. Welcome to one more EuroStruct talk. It's a pleasure to be with you for one more hour and 10 minutes. And today we have our esteemed guest, Professor Paulo Lourenço. It will be very fruitful discussion and presentation about a very relevant topic. Also with me is Andreas Lampropoulos, and I would like to welcome Andreas for also moderating this session with me. And I would like also to acknowledge University of Minho and ISISE for supporting with all the platform and Zoom and so on. Also, I'd like to acknowledge IAPSE and FIB for supporting the dissemination activities, and in this case, the EuroStruct talks. And finally, Boutique for all the design and all the efforts that they made with us during the design of all the stuff. So thank you again. I will only kindly give you some information concerning the procedure on how to put questions to Professor Lourenço. For those that are assisting us on the Facebook, you can put questions directly on the Facebook on a message. For those that are here with us in a Zoom, you should place your questions in the chat of the Zoom. So in the chat, there is an account called EuroStruct Association account, and you should direct your questions to EuroStruct Association account, and myself and Andreas will place these questions to Professor Paulo Lourenço. To finalize, I would only like to say that you are with your micro turned off and also the camera. So if you wish, when placing your questions, you can place your name also, and we can refer the name and the institution. And so I wish you a very fruitful discussion and meeting today, a very fruitful talk. And now I'm going to ask Andreas to present our esteemed guest today. And Andreas, now the floor is with yours.
Thank you very much, Jose, and thank you for your invitation. So hello everyone, and welcome to this session. My name is Andreas Lampropoulos, and I'm a principal lecturer in civil engineering at the University of Brighton in the UK. It's a great pleasure today and privilege to have the opportunity to introduce Professor Paula Lourenço in today's webinar. Paula Lourenço is one of the speakers who probably doesn't need an introduction. I believe you are aware of his exceptional work in the field of novel masonry products and earthquake engineering, so I will be quite brief. Professor Paula Lourenço is a full professor in the Department of Civil Engineering at the University of Minho and head of the Institute of Sustainability and Innovation in Structural Engineering, which has around 200 researchers and something like 20 million euros of contracted funding. And he is also currently the project team leader for the revision of the European Masonry Code, Eurocode 6, Part 1.1. He specializes in the area of structural repair, conservation, and strengthening, with works in more than 100 monuments worldwide. He's the editor of the International Journal of Architectural Heritage and coordinator of the European Master on Structural Analysis of Monuments and Historical Constructions, which has awarded an European Heritage Award in 2017. Professor Lourenço has been awarded also an ERC advanced grant of 3 million euros on seismic assessment of the built cultural heritage. He has supervised numerous PhD students, more than 50. He has an H index factor of more than 50, and he's the author of more than 1,500 publications. Clearly, I could mention a number of other aspects and highlights, but I do not want to take more of your time. So please join me in welcoming Paolo today in the webinar entitled Conservation of the Built Cultural Heritage, Earthquakes, Methodology, Research, Applications, Challenges of the Digital Age, and more. So thank you, Paolo. It's time for you.
Okay, so thank you very much, Andreas, for the introduction, and Jose Matos for the kind invitation to be here this afternoon. I'll try to give you briefly a fast overview of some of the activities we have been doing in the recent years related to the built cultural heritage. And so I will start with a very simple introduction on the fact that, of course, what we built is subjected to natural and man-made hazards. There are some concerns that the hazard is increasing in some cases due to climate change. Also for deliberate human action, where we have much more destructive power that we had in the past. I always understand myself as let's say, a technical expert, as an engineer. And engineers tend to have extremely good skills in using assessment and diagnosis tools. They have far less skills normally in involving the society and transmitting the idea of risk and the risk we are subjected to. And they are also less good in defining solutions and implementation plans. And this has to be done with the society. And here you have a picture of the cost of disasters in the last 50 years or more. And as you can see, the cost has grown exponentially. And this is a major problem for society, because if you have a big disaster, then we all have to pay it as taxpayers. If you have a small disaster, then it's your problem, you have to pay it. But whenever there's a big disaster, that's a societal problem, and it will be paid by all of us as taxpayers. So we have this difficult mathematical problem, which is huge consequences and very low probability of occurrence, which, as you know, from a mathematical point of view, this is an indeterminate quantity. And we need to do much better in communicating, and we need to do much better in defining implementation plans. I'll be talking about earthquakes. Earthquakes is not the most costly disaster, but it's the one that is killing more people in the world. And so if you think about 40% of deaths from natural disasters are resulting from earthquakes. If you also note that more than a half of these deaths are coming from masonry buildings, and that most of our built heritage is unreinforced masonry, is traditional old buildings, then you can see that I'll be talking about, well, the most recurrent typology and the most killing typology in the world due to a natural disaster. In Portugal, we have this image of 1755 earthquake, sometimes called the perfect disaster, because you have an earthquake, a tsunami, and a fire all together. And it had a huge impact, not only in earthquake engineering, but in society. So there are painters, there are the most important philosophers of that time. They all wrote about the Lisbon earthquake as the wrath of God and as something that people could not understand why it happened. So why need mankind or the population had to be punished by such a large disaster? Now, I would like to contribute to make structure safer. I'm going to show you two shaking table tests. This one, both of them are in the shaking table, the largest shaking table in Portugal, in Lisbon, in the National Lab. This one involving the University of Porto. And this is just a facade with two retaining walls, subjected to an earthquake normal to the main facade. And if you see that you have such a brittle material with a weak bond, that in the end you have nothing. You kill the people inside, you kill the people outside in the street, and you lose all property. Now, cultural heritage buildings are rather vulnerable because they were not designed for extreme events. They are normally heavy, they are very weakly connected, and they are made with materials with very low tensile strength. Now, we can make it much better. This is a test that we did also in the shaking table. It's a little bit loud, but I think you can hear the noise of the earthquake. You can see one pier collapsing out of plane, and it's a very nice image because you can see the movement in plane, and you can see the amplification of the higher modes out of plane in the upper part of the building. Now, this is a strengthened building that the only thing we did was to connect the floors with the walls. We connect an external steel plate and the tie, the joists of the timber floor, and we connect on the sides, because there is a neighbor, we connect it using a steel angle. By doing this, which is a very inexpensive operation, we increase the resistance of the building more than 50%. Okay, so if you want this to make this building safer, I always say that we just need, well, there's basically 3 solutions, and the solution is connect, connect, and connect. So we have to be sure that we have all the building parts connected. Now, when we talk about cultural heritage, we're talking about buildings that have some value for the society. There are many aspects about value and significance, but maybe these are 2 of the most important ones. One is identity, why we define ourselves as a citizen of a certain part of the world. And so I normally say that we are what we build. And so the building heritage is part of our past. If you have no past, you have no future. The second point, and so there's a lot of pressure for the society to keep these buildings. The second point is economy. And well, as you can see, tourism is a major part of the wealth of the world and of the wealth of Europe. We have 10% of the wealth of Europe due to tourism. Portugal is a very small country. There's many countries, cities in the world, more than 50, that are larger than Portugal. And we received twice our populations as tourists per year. So Portugal, being such a small country, is in top 10 of the world tourist destinations and receives more than 20 million people as tourists per year. And so Portugal and many countries of Europe will have a very difficult time without the money from the tourism. Now, having understood some of the problems we have with cultural heritage, having understood about the significance and the importance, let's go very briefly about how we handle this problem. Imagine we have this very simple building, 2 walls and a barrel vault. A barrel vault, to keep its shape, needs horizontal forces, needs thrusts in the supports. Otherwise, it becomes flat as a sheet of paper. Now, these thrusts will have to go to the walls and then to the foundations. If the walls are too weak, they will open up, and then there will be cracks in the system. Now, what you can do? You can add buttresses. These are very ugly, designed by an engineer, but we can make them very beautiful. You can add foundations. The foundations are always terrible. Most of the time, they are very weak foundations. A lot of time, there are no foundations, actually. So they are very different from what we do today. Well, of course, you can bring the weight of the building to deeper strata to make it more stable and find better quality soil. You can understand the building is very weak intrinsically, it's too slender, and we need to make it stronger. And you can make all of this together. And the message I would like to tell you today is, if you forget everything else I said, don't forget this picture. This is what we do not want to do. This is a destruction of the built cultural heritage, and this is totally in opposition with the methodology we try to apply today to these buildings. So the methodology is typically, well, do nothing, maybe just do monitoring, and you can check if there are progressive damage. Maybe you can install something like a very simple strengthening system or a stabilization system, and even monitor this stabilization system like a tie, and see if you need something else in the long term. Okay? And so we have these 2, let's say, opposing views. The old view, which is forget about what you have mistrust or distrust in anything that you have. I want to have something new. I only believe in new materials, and I don't believe in existing structural components. And the modern approach, which is try to do as little as possible. So adopt an incremental, minimal intrusive approach, ideally reversible, and we just do what you need. So the best possible optimization is the one involving less resources and, let's say, less harmful for the cultural heritage value. Now, this is an extremely young field of science. So if you think about civilization, we talk about 10,000 years old. Well, by the first quarter of the last century, people believe in things that we don't believe anymore, like using materials that are non-proofed in terms of durability, in terms of compatibility. Like, for example, believing that the new materials and the new additions to the structure should be hidden. And only 30 years after, which is a microsecond in the story of civilization or built heritage, we changed our minds totally. So now we'd like to use traditional materials and techniques if we want. Now we should be able to distinguish what we make today from what was there, okay? And so there's still much to do. And normally what I say in a very simple way is that we are doctors of the built heritage. And so we would like to approach the procedure very similar to medicine. So we try to reconstitute the history of the building, make the necessary exams like the doctor does, make a diagnosis. If there's no diagnosis, there is no therapy, and then make the therapy once you have the diagnosis. So most of us would be very happy if the doctor says, you're fine, you need nothing, okay? I think all of us would still be very fine if the doctor would say, you need to take this pill. But if the doctor will tell you, well, I'm going to do this very complicated surgery, maybe 50% of the people die out of this surgery, I think all of us would like to have a second opinion. So we believe the building is entitled to a second opinion if you want to make a massive intervention. And the final comparison point, which is very important, is about control. So going back to the building. And so the doctor will tell you, go back, come here in 6 months, in 1 year, 2 years, we make new exams. So we would like to go back to the building and monitor as a patient, okay? Now, research in the field is today as advanced as any other field in civil engineering. So it was underdeveloped for a long time, but today we are able to do everything like we do for concrete, like we do for steel, for modern materials. So we have characterization at all scales. We have very exciting new techniques, very similar to the ones in medicine. We use different principles to see what cannot be seen, to hear what cannot be heard, okay, to measure vibrations that we cannot feel. And so we have exciting new tools that allows us to do anything, or almost anything. Also from the computational point of view, we move from very different models that would take 1 year to make of a full building to amazing things that we can do today that, I mean, my students in 3 months, they are able to model a full building and to do nonlinear pushover and nonlinear dynamic analysis. And so we have the tools to do it fast from the modeling point of view. We have the tools to make it fast from the analysis point of view. And we have exciting new materials that we can blend with traditional materials. For example, I like very much the picture in the left, where you can see that's not too different from putting a prosthesis in a human body. So we do the minimum we can, okay? Now, I'm going to show you some of the examples that we have been doing. I'm extremely happy that we're able to combine high-level research with engineering. I think that's fundamental in modern academia. We cannot have only professors that have no link to the engineering practice and to engineering world. And I'm very happy that we are able to do it. This is one of the most exciting buildings I worked, which is not masonry, but I couldn't resist to put it here. Now, it was masonry, and then there was a fire, there was a revolution, and there was an earthquake, and we lost the building. And then they built it again. And then there was another earthquake, and they lost it again. And they said, well, masonry is no good, so let's make it in timber. And then there was timber deterioration, there was another earthquake, and they lost it again. And finally, they decided to make it in steel. And so we have a Gothic or neo-Gothic building, which is modern and made of steel, replicating and mimicking a building of the 15th or 14th or 16th century, which is very unusual. And it's also a story of structural failure. So we had already 3 failures with the building. Now, the problem is that, well, metals suffer corrosion. And so there's important corrosion in the building, and we'd like not to have a 4th failure. So what we did was, of course, to do inspection of the building, to do in situ testing. And then I like this image because it tells us the complexities. A model is a product of our imagination. If you don't validate the model, the reliability of the model is 0, is meaningless. So you can see here that we started with model 1. Then we did many trials, which cost a few months actually, until we were happy with our model, which was model number 5, and increased significantly the size and increased significantly the elements we brought into the structural model. This is typical of existing heritage, where the structure and the non-structural components are not so separate as in modern buildings. And then we did a typical structural analysis saying that the building is okay, but you need to stop corrosion, otherwise it will not be okay in the future. Second example of using these tools, this is a hyper-complex building in Peru, which is a mix of masonry, adobe or earth construction, and timber structure, all combined together. It suffered 2 earthquakes, it's heavily damaged. It is expected that the reconstruction starts next year. We were involved in assessing the safety and in designing the strengthening system so that we will try to do it using traditional techniques. I will not go into detail. I would like to tell you something which I think is fundamental from the point of view of engineering. I had a meeting with the local community, with local engineers, the local authorities, where they were saying, we don't want this building anymore. We want a reinforced concrete building because we're afraid it's going to collapse. And they made a very, very important statement, which was, why should we be forced to use a building which has less safety than a modern building, and why we should have to face the risk of a higher probability of failure? Which I think is a very important science, a very important question that the society is allowed to make, and we should not accept that the level of risk is much higher than a modern building. Of course, you can reduce the number of people inside, you can remove elements from the inside in order to reduce the exposure. But what we tried to do was to convince them that with a new intervention, the building would have a comparable level of safety with a modern building. Okay, and I believe we're able to do it by using adequate tools for the strengthened model. Okay, now a couple of examples. I know I have only 5 minutes, but I think I'll be more or less on time, about other possibilities we use, not at the building level, but at the structural level. When you study a monument like I showed you, or an important building, we are allowed to use very sophisticated tools. When we're looking to a city or to the world, the tools have to be different. I don't care if I predict the behavior of an isolating building wrong. That's not relevant. What I want to address is the building stock in average and understand the global behavior of a building stock. So I use very, very simple tools. And what can I do? I can use tools that allow me, for example, to know if there is a seismic event with this given intensity, how many buildings will be collapsing, how many buildings we cannot use, how many people will be dead, and how many people will be homeless. This is fundamental for civil protection and for being prepared, because I need to know how many tents I need for temporary housing. I need to know how many hospitals, how many beds, and we are able to give you this information immediately once you have a disaster. We can make these scenarios and helping civil protection to make a decision on how much is needed in case of a disaster. We are also able to tell you if you use different strengthening tools, for example, strengthening tools like for stiffening or to connect walls to walls by using ties, what is the influence? So I have here scenarios that if, for example, well, I have given vulnerability in the building stock by introducing a certain strengthening combination, I can reduce this vulnerability. I can tell you exactly, on average, how less people will be killed. I can tell you how less buildings will be collapsed, okay? How less beds you need. I can even tell you if an investment is profitable or non-profitable. And that is fine. I don't think as a society, an investment has to be profitable. We may assume that we're going to lose money, but we're going to save lives. Or we can take the alternative decision and say, this is not economically viable. It's a decision. But if you have no information, you cannot make this decision. And we can also do this, which is essential, which is support emergency planning. If you have a disaster, you need to be sure the firemen can go in, the ambulances can go in, people can go out. If everything is blocked, not only people are killed immediately, but people are killed afterwards because you cannot provide any help. And so you can do, for example, selective interventions, and you can be sure that this yellow area which is fully blocked, by acting with far less money, you'll have sufficient evacuation routes for people to use. Okay, so these are some of the activities we have been doing at this territorial level. I will finish with several fast provocative statements. Today, everything is about digital. This is a terrible and nice web conference. It's very nice that we have these amazing communication tools, but nothing will replace the coffee breaks or the dinners or having contact, physical contact. But the future is digital, and this we cannot avoid. So there's many things we can do. For example, in survey, today using drones is super inexpensive. We can basically access places that we would never be able to access in another way, in very, very simple way. This is a building in Mozambique that we are working, and I can see things now in my office being, well, 14 hours flight away or 18 hours flight away. I can also use these amazing 360 cameras that we take every time, because then I can see things in my office. I've been there. I don't believe you can do inspection from far away, but I can then look more carefully in my office by using these amazing, inexpensive tools. I can even build models in a very cheap, easy way by putting this all together. I can even use photos, crowdsourcing from different people from the internet to have a 3D model without being concerned about anymore so much on calibration and other things, right? Quality of pictures, etc. And I can use tools that bring this virtual model, for example, as a point cloud to something physical. And then I can do things like this, for example, obtain order photos and plans and use them to map. This is very important. Use them to find deformation and movements in the building. I show you here very interesting, I think, safety assessment of the Guimarães Castle. And here what we did was to use laser scan, combining the depth of the scan with intensity. And we were able to obtain, for example, automatically what is the size of each stone. Then we put it in our numerical model, and I can tell you the safety by using a very simple model, either discretizing all stone, which I don't want to do, or using something homogeneous where I put the geometry in another simple way. Okay. Another example of using these tools, trying to make them interoperability, that you can operate all of them together, different softwares made together, and would like to have the real object, a cloud of points, and automatically almost a sort of structural analysis, simple, that we can make. This will never replace the engineer. The engineer remains fundamental because the experience cannot be replaced by a computer yet, but it's something that will make our life easier. Another thing which I think is very, very important is using geographic data. Here I show an example of the tool I showed you before at territorial level by using free software available in the net. And so we try to use, instead of sending people, teams to a city center, historic city center. In this case, we use different tools available in the internet. We made a comparison, what you can get, you cannot get. Of course, there's always better you can do physically, but there's many things you can get from a tool that is based on remote sensing. And you can see here the difference where I compare a 1 week work with 2-person month work. Okay, I'm not saying the quality is the same, but I'm saying this is also the way to go, at least in the first screen. Then in situ testing, monitoring, damage detection, there's many tools we can use today. Now, for example, the use of dynamic identification and ambient vibration tests is very cheap, very easy to apply. I show you here an example of a damaged tower, and we measure the tower before and after. You can see the huge impact, for example, in the change of frequencies. On average, as you can see, the change of frequencies in these two columns, they change about, as you can see, 50%. So it's a very large change because of the actions we did with the strengthening. And we can see this clearly in the modes, so that the modes of the structure before repairing, where they were all crazy with many parts of the structure moving independently. And then you can see the beautiful modes in the structure after repairing, where you have full integral behavior of the structure. So these tools can assess the global behavior of the building, can provide us with amazing information. They are now very inexpensive to use and relatively easy to install in a building and to use them to monitor the structure health. Okay, I think this is the final pictures I'm going to show you. We had a very nice project funded by the Interreg program on preventive conservation. And so why do we believe that we have to go to the doctor and that our car has to go to the doctor and our buildings don't have to go to the doctor? That's a very strange thing, but this is reality. And so we developed a methodology to be used in the long term for cultural heritage buildings via some non-profit associations that have 3 service levels. One very simple with basically yearly inspections. One more complicated that involves already monitoring and a more detailed survey. And another super complicated integrating a BIM with an historic building. And this is one example of such a building. So you can do very simple inspections annually at relatively low cost that provides you a simple report. This is mostly fully automatic. It's traditional we use for the built heritage, for bridges, for highways, for most of our built infrastructure that is being monitored with a class number and some condition classification. And then you get a very simple yearly report saying if it's good, if it's less good, or if it's terrible, and you have to do something about it. Then you can do a little bit more detail, and you can already have monitor to the building. And this is the Castle of Guimarães, where we had a more sophisticated survey. Then we had monitoring to the building, and we are, let's say, providing a closer observation of the structure health of the building, and we can go for full integration using a building information modeling approach, which here we also have for this building, where everything is integrating in a unique virtual model. Okay. Now, needs and directions in the digital world. There's amazing things we'll be able to do, and we are already doing. For example, for vulnerability mapping, for soil settlements, all of it using satellite imaging, using, street views, and more digital tools. And I believe strongly this will change the way we'll assess the risk at a very large level. There's still much we have to do in graphics processing. Things are getting amazing. We still have problems in speed, in the need for having very fast computers and very good graphical cards. And then we have the problem that what you see is not really what you have. And so we have to combine what you see with additional tools to have a structural model that makes sense. Now we still do the more we have, the more crazy we do. And so we are now moving to analyze multi-million models. And so we have, as you can see here, crazy stuff. And we are doing here huge models at a small level and huge models at a large level, where we try to address very complicated models. And so there's a lot of still we have to do in having adequate constitutive model and adequate hardware tools. And also inverse problems are a key issue. It's a very difficult nonlinear problem. These are examples of tomography. And this means also model updating based on information that you measure from the building, which is also a key issue for the future. So there's many things we will be using in the next years, exciting buzzwords of today that they will be used in structural engineering for sure in all these tools. Also computer vision, it's an exciting new world. This is the new shipping table that will be available at the University of Minho with a unique 6-camera single model, 3D view of a model by using 6 cameras independently and combining a DIC model real time in the computer. And this is the end. So thank you for your time. I'll be very happy to entertain questions. I think the field, as I wrote here, is exciting of the built cultural heritage. Risk management of the built cultural heritage is an issue. We do have a problem on bringing this problem to society. The digital tools will be, I think, essential in the near future to make things cheaper and more reliable. I end up with 3 very complicated problems, in my view. One problem is when you do risk management, there is the problem of money. And if you would say that the Tower of Pisa has infinite value, you cannot put infinite in your model. And so you end up with a problem that you cannot address scientifically. A second problem is everybody say prevention pays. There are numbers. I put you here from the National Institute of Building Science. €1 saves €6. That's very simple to say, but the society doesn't believe us. Then, well, the other point, which I think is as a whole for EuroStruct and for the engineering community as a whole, the amount of knowledge we have today is amazing. I think we know so much. The question is, how can we bring this to a safer society and a more reliable risk management in the field of cultural heritage building? So thank you very much for your attention.
Thank you, Paulo. It was indeed a very interesting and challenging talk. Just before starting with the first questions, I want to give you some information. So for those who are willing to place questions to Paulo, you can either do it on a Facebook or here in the Zoom by sending the question on a chat. You have here the chat in the Zoom, and you need to send your question to the EuroStruct Association account, or either to me or to Andreas. So we'll be able to pick your question and place your question to Paulo. Also, you are with the micros and the camera is turned off, so we can see some of your faces, which is very welcome. But the only way that we can put your questions to Paulo is through the chat in the Zoom or in a Facebook. So I'm going to start with the first question. We have here some questions from the audience, but I want to put myself a question which I believe is a very relevant question nowadays, which is something that Paulo raised in the beginning of his presentation concerning the communication. What is happening and what can we do in order to make society more prepared? Because I believe, Paulo, you are running SAC, you are running as a professor in academia, you also have contact with industry. How should we better communicate in order to make the society in general more prepared for those issues that we face in engineering field with a very low likelihood, but with large consequences?
Yeah, I think well, thank you for the question. It's a very difficult question to answer. It's not a problem of Portugal, or I think a given country. I believe it's a problem of most countries. Normally, when you have an extreme event, like it doesn't matter, but it could be the fire at Notre Dame, or it could be the tsunami in Southeast Asia. Of course, the instantaneous impact is enormous because of all the social, not only the social networks, but also the ability of the information to travel extremely fast, or let's say on real time. The problem is that next week there's something new and something different. And so the society has this strong impact, but I don't think nobody remembers anymore the Notre Dame fire, for example, or any other major event, because there's always a next event. And so I think we have two problems. One problem, I mean, I can see it from two perspectives. One problem is the authorities understanding the problem. The authorities have a responsibility, and responsibility is to lead, in my understanding. If you are the head of something, or if you are the prime minister, you are bound to make decisions, and this is, in a way, it's a gift, but it's also a burden, and you will have to make a decision. And so I think the authorities should realize that if the level of risk is unacceptable, we have to do something about it. The second issue is, of course, if authorities are unwilling, is then the society as a fourth power, then it means dissemination, and it should be pressure from the societal point of view. Okay, I think this can be done on both sides. Now the question is, we normally have difficulties to communicate as engineers, and I mean we are mostly technicians. Often it's not easy to speak to news reporters, and so this could be done by international associations, I think, more effectively. Maybe also with the help of experts in the field, because we are not definitely experts, but this could be things like EuroStruct or IAPSI or Portuguese Society of Engineers and others that should invest, I think, a reasonable amount of money in disseminating this. We have knowledge, and if the risk is not acceptable, we have to do something. Now, to give you examples of things that might work. For example, if you think about earthquake, and if you think the risk is too high, or if you have the measurements to tell you that the risk is unacceptable, well, it's evident that you cannot solve the problem in 1 year or in 2 years. Maybe you need, 20 years or 50 years, and this is fine because the risk is not immediate, no? So the probability increases obviously as the time goes more extended. And in many countries this happens. No? So normally it's very difficult for a government to say, let's force everybody to do rehabilitation because the cost is horrendous. No? But if you have a plan for 20 or 30 years, for example, in Italy now, you can get the credit back. So if you put money for the seismic strengthening or retrofitting, then you can get it back from your taxes. And that's a very simple way from the government. It's not putting any money. There's two ways to do it. Either it's compulsory, and if you do works above a certain cost, as it is now in Portugal. So if your cost of rehabilitation of a building, it depends if it's 50%, if it's 30%, or whatever that is, you'll have to comply with modern regulations. So the building, for example, has to be earthquake safe. That's one way. But if you have no actions, so if you're not renovating the building, then the risk remains unacceptable. For example, in the US, because the cost again of renovation is so high, if you go to California, you'll see in several buildings that they have a label saying that this is an unreinforced masonry building. It's unsafe in case of an earthquake. So if you like, you enter. If you don't like, you don't enter. Of course, it can be a little bit of a problem in some cases if you have recurrent earthquakes to sell it, okay? So this can be done compulsory when you want to sell it, okay? And this can be done with a tax credit, so that, let's say, somehow you're subsidizing the intervention. I think it's possible. The question is, if you are an authority in the short term and you think in a 4-year mandate, then discussing 50 years scenario is not relevant. No? So if you're talking about climate change, it does not make any sense to talk about climate change in 4 years or in 5 years. No? But climate change gets a lot of pressure from the society and actions are being made. So the question is, why is earthquake not? Why is the collapse of bridges in the US and in many other countries? I mean, the condition of the infrastructure in some countries is ridiculous. I mean, of the transportation infrastructure is unacceptable from my point of view. And nobody cares. So why people care about climate change and people don't care about the infrastructure condition? In my view, because of the pressure from the media. So we have to do something about it.
Thank you, Paulo. Now I'm going to ask Andreas to place the next question. Andreas, your micro is unmuted, please.
Yes, thank you, Jose, and thank you, Paulo, for this brilliant presentation. It was a great overview of the recent advances in the field. So clearly we can have a long discussion and there are a lot of different topics covered, but we have quite limited time. I have a few questions here, and I have another question I wanted to ask you, so I will try to combine those. So we know that when we're dealing with cultural heritage, there are a lot of restrictions in the materials we are allowed to use, as you mentioned also at the beginning, and what we should do. Shall we do something similar to the existing structure? Shall we do something different? And nowadays we have a lot of recent developments in new construction materials, high performance materials. I can see some of the questions in the chat also mention the CFRPs, the NSM, fiber reinforced polymers, or I can also mention the high performance concretes. So what are the, I know that it's really hard to call ideal materials for heritage because we know that probably each structure is different and we should deal each structure independently. But what are the materials we should be looking for when we're dealing with monuments and cultural heritage? And what are the main restrictions in this area? And also, I would like to link that to any code provisions. So do we have any code provisions that we should follow in order to make things easier and get easier the permissions from the local authorities?
Okay. Well, thank you. It's a super complex question because it's many points together. So let's start maybe by the last part. So normally a cultural heritage intervention must be approved by a local authority. It depends on the country, but whenever, for example, if you have a UNESCO World Heritage Site, or if you have any declared monument in your country, then there is the monument and the buffer zone. And so within the monument and within an area next to the monument, which will have an impact in the monument, you cannot do anything without an approval, okay? From my experience, for example, in the works I've been doing, I never had problems with the authorities. And so I think if you do a good job, this should not be an issue. Of course, if you are doing things in opposition, which is the modern understanding, then you end up with a problem and this will not be accepted. Now, a second point is, do we have codes? And my answer would be no. So there are some recommendations, for example, in Italy. Italy is very active from the technical point of view. They have a lot of built cultural heritage also, but there are guidelines for intervention. But in most countries, if you have a listed building, so something which is declared internationally or nationally as a monument, then no codes are applicable. Okay, so this includes not only the structural codes, but all the other ones like acoustics, thermal, accessibility, etc. So we have to understand that, well, I'm a structural engineer. I tend to concern more about structures, but a building is not only a structure. So, I mean, if the building is safe, but you cannot use it because it's too cold or because the noise is unacceptable and you are always fighting with your neighbor, that's not a good building. And so we have to compromise. And if you try to apply modern regulations to many buildings, many of the things are impossible from the thermal point of view, from the acoustic, accessibility, for example. If you need to have, you know, a lift, this can be a problem. If you need to have, you know, a WC where handicapped people can access, this can be a problem in many conditions. And so we have to be careful in using modern legislation, modern codes. I think we should be relatively flexible, but in terms of cultural heritage, from my understanding, no country will enforce you to follow it. Now, from the pure structural perspective, before going to the materials, which I will address soon or next, there is a very important issue in my view, which is who takes the liability? Because if you are the structural designer, you are supposed to take the liability. So in many countries, you have to sign a liability statement, which will have consequences that can either make you bankrupt or go to jail in case the building collapses and kills people, for example. And so that's a very important issue. And I think it's unfair that it should be the structural engineer to take the full liability. Okay, and so the concept of, let's say, improvement is clear. And for example, there's an ISO norm on existing buildings, which says something like, if a building demonstrated in the past that it's okay, I mean, you have to be careful in saying that it's unsafe, which is evident. If you have a building with 300 years and you go there and say it's unsafe and the building shows no sign of damage, of course it can be unsafe for an extreme event. But you cannot say it is unsafe for gravity loading. Does not make any sense because it has been there and it has proved by time. And so that's a complicated issue on liability and on safety level that in most cases, I believe, remains in a relatively gray area of our field. Despite all the, let's say, the conceptual and theoretical things like you can do, for example, with the Joint Code on Structural Safety, where you can do more advanced safety levels. I mean, all of this, there is a context, but sometimes the context is a little bit independent from reality. Now, going to the point of materials and techniques. I normally say, maybe I'm too optimistic, there are no bad materials and no bad techniques, almost. There are only bad engineers. And I mean, I can show you horrible interventions by using a traditional material. I can show you interventions that I would be ashamed if I would be the designer by using masonry, which are obtrusive, they destroy the building and make absolutely no sense. Like you put a column in the center of an arch. Come on, this is ridiculous. And there's many of those. Or you put the tie in the middle. If you take a church with 3 naves, then normally the columns are like this because the upper nave puts the columns outside. The lower naves put the columns inside. The columns are like this. Then you see horrible buildings with straight struts made of masonry here. Okay, this is horrible. And it's made of a traditional material, traditional technique. So it's not, for me, it's not a discussion if the material is good or bad. It's how you use it. Now, the philosophy today is if you can do it with traditional materials, you should use them. So I use timber, I use stone, I use lime mortars, I have no problem. The problem is, in many cases, or in some cases, you cannot do it in a safe way because the traditional materials will not provide you with the adequate safety level. For example, I use a lot of lime-based grouts or injections. This is a material like water. The maximum size of the aggregate is 100 micro, or 0.1 millimeter is water. Whatever you will see, if there is a crack you don't see, you inject, you'll see the grout coming out. Now, this did not exist in the past, obviously. It's a modern material. It's lime-based. It's exciting new material in my view. I use it often. Of course, you cannot remove it in the end, but I think it's compatible. And why not using it if you think it's needed? Okay. So you need, of course, to combine the theory, which is you like to use a material which is reversible. You like to use a material that is compatible, and compatible is a nightmare word because it means physical compatibility. It means mechanical compatibility. It means chemical compatibility. So it's too much compatibility. And you'd like to have also, let's say, something which is durable. And so these are too many things you can do. If I inject, I'm sorry, I'm not going to get it out, never. I use a lot of stainless steel. I use the most expensive one, 316. I'm sorry, but I use very little quantities. So this is the same material you use, you know, in medicine. And I use very little amount. So this is not increasing my costs. So why I'm going to use, you know, regular low carbon steel or regular, you know, 304? This does not make any sense. And stainless steel is certainly not traditional. And now talking about the modern materials. Most of the community, I'm talking about masonry here, not concrete. Most of the community has a lot of problems with glued materials, epoxy-based. Because epoxy is water vapor impermeable. Epoxy has, you know, thermal expansion coefficients very different from masonry normally, and it's a problem. So it debonds easily. You're gluing it to a very weak substrate with a lot of salts, with a lot of humidity that will remain, and so it's not a good idea. For example, CFRP or well, GFAP, that you apply it as externally body reinforcement is almost forbidden in Europe, like reinforced concrete. Reinforced concrete traditionally is non-durable, not because of the concrete, but because of reinforcement. It introduces salt, it introduces something which is water vapor and water impermeable, basically, so it's a problem. And I see CFRP glued in developing countries. In Europe, I don't see it anymore. It will be very difficult to have a project approved with CFRP glued or concrete. Now, the new exciting, for example, a new exciting material, which is still very modern, is TRM, or combining glass or now, well, natural fibers are in discussion. It will take a few decades, most likely. But either use glass fibers or carbon fibers inside a net using a lime high performance based mortar. And so you basically have a reinforced plaster. Okay. Now, this I'm talking about monuments, which is different from a small house in a city center where you have a lot of flexibility. So again, my point is there are really no bad materials. I think most of them we can use, but you have to use them wisely.
Thank you very much for a very detailed response, so very helpful. Jose, would you like to continue?
Yeah, I'm gonna make now the next question. So we have several questions from the audience now, and the question that I want to put to you, Paulo, is regarding the data. Is it a question from the audience concerning how do you deal with the lack of data? I will only make an achievement here, and in most times poor data, when you are working on extremely important heritage structures.
Okay, I mean, our approach says something that I like very much. So I was involved in a document issued by e-commerce that somehow provides the framework for the modern scientific approach. And it has two, I think, very important statements, which is, well, maybe three. One is you have to issue a detailed report. So you have to make a report that justifies your assumptions and justifies your decision. And this report, the owner in a very important monument, particularly if you're suggesting something which can be detrimental for the building, is entitled to confrontation. And so he, in my view, should ask for a second opinion. And so that's an important process of an important part of the decision process, in my view. And the report should be able to be understood by the authorities for someone which is an architect, an archaeologist, a building owner, okay? In case of very important monuments. The second thing we also say is that experience is very important. And so the personal judgment is very important. This means that people have to be trained. We have engineers, we have architects, most of them have very limited information, traditional materials, traditional techniques, because they never studied them. That's okay, because you can study them by yourself. I don't think that all the education has to be formal with a degree. I mean, if you are an engineer, a licensed or a degree, you are entitled to continue to study. The more you study, the more you know. I learn every day. So I hope my colleagues do the same. And so you can learn, there's a lot of information available. But the experience is very important, and we make this very clear that judgment is a fundamental part of the process. The final point, we also discuss uncertainty, and we say clearly that there's too much uncertainty in the process. Now, what do we do to reduce uncertainty? We do many things. For example, when we look at safety, we basically use a process that we don't define safety based on a numerical model. I don't believe in safety based only on calculations. So we use a process that uses 4 components, and the 4 components are the history, so how the building performed in the past, okay? The inspection and the monitoring, how you see it now. You use a numerical modeling, and you use sometimes testing. And so testing can be a load-proof test, for example, if this is possible. Or it can be also the monitoring and the long performance of the building. Now, These 4 components should give you information which is adequate to make your judgment. So if you only believe in the numerical model, if the numerical model is not assessed, in my view, your judgment is irrelevant. So if your numerical model tells you, for example, this building subjected to gravity loading should collapse, well, I'm sorry, because the building is standing. And so something has to be wrong in your approach. And so we combine the 4 components: understanding the past, let's say, obtaining information for the present with all the tools, having a model that we validate, okay? If you don't validate, the model is useless. And so we can validate, for example, by checking the stresses in situ, by using flat jacks tests or small elements you put inside of the building to see the pressure. We can use many tools, for example, to see what you have inside. We can use sonic testing to obtain information about the elastic properties. We can use dynamic identification to get global information of the building, also on the elastic properties. So there's many things we can do. We can apply the loads, the gravitational loads, and see how the building performs and compare with the building. We can apply a past earthquake, a past flood, a past whatever hurricane, and see how the building performs in the model and how it performed in the past. So you validate the model. Once you validate the model, you can use it for predictions, okay? And so I believe that using this combination, okay, we make our best guess. I will never say that our best guess is correct, but I'm saying that our best guess is our possible action towards a very complicated problem. I normally also tell, well, my students, and often and sometimes in public conferences, that you can have all tools in the world, okay, but the 2 most important tools can be trained, and the 2 most important tools are our eyes and our mind, okay? Our eyes are trained by experience, are trained by the assistance of more senior partners, are trained by going to the job site and learning from the different people involved. When I go to a different country, I see things often that I've never seen. So I have to ask. And every time I see something different, I learn a little bit, okay? And so a trained eye will tell you if maybe there are voids inside, or maybe there would be. I remember, for example, one of the first things I did when I was a bit younger, last millennia still, I went to a chimney. And there was a chimney with maybe, I don't remember, 18 meters high. And there was a vault on top, a big opening, 4.5 meters span. And there was a granite lintel. And I said, there's no way this lintel is taking the chimney. That's impossible. So I opened up the structure from the back, and there was an arch inside. So there's many things in an historic building or an existing building that you cannot see. But if you know traditional building materials, traditional building technologies, there's many things you imagine and you can validate, okay? So I think our guesses are quite good. And I'm very happy with the things I've been doing in the past, in the sense that I feel comfortable with the decisions we made.
Thank you, Paulo. Now, Andreas, please.
Thank you, Jose. Paulo, I would like to have a follow-up question. So you mentioned that, as you correctly say, it is important to do this training, to validate the models we have, calibrate with data. But how easy is it to do when we are talking about cultural heritage, where we cannot really take any, I believe, any course or do any destructive testing? So is it something that we can easily do when we are talking with monuments? I was also very much impressed by your work on the territorial level, where you presented this fantastic, I believe it's quite complex process on how to assess vulnerability and then take into account different strengthening techniques in order to reduce the vulnerability and also calculate the cost, which will be a fantastic tool. And I believe this will need a lot of training too. So how easy is it to do this kind of training and validate and calibrate your models when we are talking about cultural heritage and monuments?
Mm-hmm. Okay, so I mean, regarding sample extraction, it depends. Also, it has evolved in the last 2 or 3 decades to my knowledge. So people are now a little bit more open. I mean, I remember when I started working in the field about, I don't know, 30 years back, that people were not so happy in taking a small sample or taking a core. That would be impossible. Things are getting a little bit easier because people understand the benefit of having a better diagnosis. If you know very little, of course, uncertainty is higher. That's it's reality. In any case, there are many tools. So I think the experience is good because the experience allows us to know a lot of things by looking at similar buildings. No, it's inductive reasoning that engineers hate, architects love. And so we can learn from our other fields of sciences, from psychology, etc. So by observation, not using the scientific method, we can learn, okay? Now, it is still possible to get a lot of data. As I said, we have georadar, we have thermography, we have sonic testing. These are things we use recurrently without any problem. We have dynamic identification, we use recurrently. I mean, whenever I go to a team, anywhere in the world, we take a lot of equipment and we do many tests. I never had a problem. These are fully non-destructive. If you want to do a flat jack test, it's a little bit destructive. If you want to get a core, it's a little bit destructive. I think it's getting better in the sense that often it is allowed with care in selected areas. But I think because of the amount that was invested, particularly in Europe, in the last few decades on testing these materials, that we have really a lot of information available. Sometimes even the information is so much that you cannot, you know, screen properly and decide which one is the good one. For example, the Italian code and even the new Euro code, part 3 for seismic assessment and design, will have a lot of details for existing building with all the data you need. For example, what is the Young's modulus? What is the weight of the masonry in my back? Okay. What is the shear strength? It is in the code now. What happens if I go to the masonry in my back and I inject, or if I put a reinforced plaster? It's also in the code. And so using a lot of data, people are adding these things to the code, okay? Because there was really a huge investment, particularly from Europe. Cultural heritage was always a priority in the funding from the European Commission, and the developments in the last decades are amazing. Now, going back to, I know I've probably taken a lot of time in the answers, but going to your last part of the question, what to do with the territorial scale? I mean, what we do, we combine, there's basically 2 approaches in a combination of the 2. Either use an empirical approach, which is whenever you have a disaster, you go and check. And some of the formulas we use, for example, the formulas I showed you in the first examples, in order to assess vulnerability, is based on a formula which is empirically based, okay? And this was obtained by a large set. So every time you have a disaster, unfortunately, you can learn from this disaster, adding it to your data set, and you have a better prediction. Hopefully, we don't have too many disasters, and so this grows slowly. Huh? Also, the scientific method is quite recent. Another possibility is to use expert-based approach. For example, I was involved with the FEMA, let's say a sort of new earthquake generation codes, where they invited 20 experts or so. They put it all together. They give us some seed questions, some of them extremely complex that, to be honest, I had no idea what was the answer. And so from our responses, they balance our weights, okay? And then they ask you to predict something, and then they took also the balanced response. And so you have an expert, and there are processes which are scientific, hopefully to get a better answer than a pure average. And so that's also a possibility. And with what we try to combine is to combine expert, but with empirical, and with numerical simulations. The numerical simulations at such a large level is the more complex, and often they are a bit off reality because it's really complicated to incorporate, you know, at this large scale, all the heterogeneity that you have in a real territory.
Thank you very much, Paulo.
Now it's my turn. I want Paulo to place a question from the audience that we are receiving. This question is with respect to the decision making, which is very pertinent. So in your opinion, what are the major achievements in terms of developing a risk assessment tools which use information from different diagnosis activities to help decision making on heritage structures? And do you believe if there is still a lot of work that needs to be done in this direction?
I mean, that's also complicated because it really depends. If you're talking at the building level, which is single, unique, I'm talking at monument level. Now, if you're talking about the historic center, I think a lot of the information that we know is applicable, but of course it is unreasonable to use the resources that you're going to use in the Tower of Pisa or in the Monastery of Jerónimos. This does not make any sense. Huh? So if you're talking about a unique monument, they normally have a very different structural typology because they are unique, and you can invest more because the level of funding is higher. Now, the decision process, we say it's objective. I don't think it's extraordinarily scientific, and I don't think it's possible to put weights at this stage. So we have these four components that I said, no? Which is information from history, information from the building, inspection, non-destructive testing, information from the structural analysis, and information from, let's say, testing. It can be dynamic identification monitoring, it can be a load-proof test, etc. You have four components. From these four components, we'd like to reach a decision. Now, if your decision is, for example, safe, unsafe, well, this is one part of the decision. If it's safe, it's fine because you say, okay, the building needs nothing. Now, if the decision is unsafe, then comes part two. And in part two, when you have to design strengthening, you'll have to decide first thing, well, something that you decide before in principle, which is what is the minimum safety level you accept, which can be lower by the code. For example, for earthquake engineering, in most countries, which also happens in the Joint Code on Structural Safety, if you have an existing building, your beta can be lower, your safety lower can be lower. Why? Because the building is there, the cost of an intervention is much higher, and because, well, it already had this history, okay? And so, but if you design, if you need to strengthen, then you have an additional complexity, which is to assess the harm you're doing to the building with the benefit you're doing to the building. And so ideally, we talk about cost-effective measures in the sense that the measure should be the minimum possible to reach your goal. But again, if you have to weight safety with cultural value, that's a nightmare. So of course, there's things you cannot do from the structural point, from the cultural heritage point of view. If you have, I don't know, frescoes in a wall, you're not going to open up the wall and destroy the frescoes. That's unacceptable. Of course, you can core the wall from something, even with frescoes, without any problem from the top. But you cannot destroy the frescoes to put something there. Even if you then put the frescoes back. This is not acceptable today. And so I don't think we can use such detailed scientific approach that we can give proper weight and the decision making is truly objective as we would like. So maybe there's ways we can try to bring, some more detailed science to this. I'm not sure if the result will be better because each case is unique and the constraints are very difficult to consider on a global level. If we're talking about territorial scale, no. Then we use all the different tools, machine learning, all artificial intelligence, of course. I mean, we train our tools, we check if they are okay by dividing the sample. So this is very simple because you have a lot of data and then you use the traditional, let's say, standard tools to process the data.
Thank you, Paulo. I'm going to put the last question from my side, and I'm going then to ask Andreas to place also the last question from his side. From my side is a question related also from the audience and related to the earthquake engineering and return period of the earthquake engineering. In assessing a monument, how you consider this return period of the seismic action when compared with other new structures? I think is a quite pertinent question.
Yeah, again, very difficult. I think anything involving safety is a nightmare. Now, if you take, for example, Eurocode Part 8 or the Italian norm, you typically design new buildings for 475-year return period. And most codes allow you to reduce this for an existing building. So typically it's 2/3 or 3/4. So you can reduce for 67% or 75% because the building exists. And in some places, this is, for example, in Italy, this can be decided at regional level, okay? I believe. And in Europe, of course, it can be decided at national level because it will be part of a national annex. Now, the different question is, if you have an existing building, what should you do? And in most countries, you'll have 3 or 4 performance levels, which can be immediate occupancy, you can use a near collapse, or you can have ultimate, associated with different return periods. It's quite complex because in order to use this criteria, you need performance levels. And so it's very simple for a reinforced concrete building, or not very simple, but okay, it's simpler to say how much is the rotation of a node, or how much is the interstory drift. Come on, if you want a historic building collapsing out of plane, nobody knows what is an acceptable drift level, okay? So if you have in-plane masonry, shear wall of masonry, we know very well the performance levels. But if you have out of plane, it's a mess. And so I would say that most people in an existing monumental building, which is unique, complex, are focused mostly at collapse. We have this new European project. We're going to do, hopefully, thousands of shaking table tests with a new exciting DIC artificial vision 3D full model or single 3D full model, where we hope we are going to other performance levels. And hopefully in 3 years or 4, I will have a different opinion. But I don't know. Maybe we will fail, because science is also made of failures, no? But each failure is also a step towards progress. No?
It's a risk. Thank you, Paulo. Now, Andreas, please put your last question.
Yes, thank you, Jose. One, I believe, is probably the last question, and is taken from the audience. I would also like to build up on this. So the question is, how can we convince people to accept monitoring instead of intervening? And if I can add to this, how do we know the right point at which we should start working on the intervention? How do we know the critical point where we should start doing a strengthening technique?
Mm-hmm. Okay. So the good thing is you only make difficult questions. Huh? It's also complex. I mean, to my understanding, normally, mathematicians and these people that you use with temporal series, they say that you need normally, 3 periods. And so you need 3 years of monitoring. Now, if you go to a client and you say, I'd like to monitor your building for 3 years, in most cases, they will say, you are crazy, man. So how come you're going to take such a long time to make a decision? Okay, the good news is that we are doing a lot of, I think, exciting things, you know, with autoregressive models and with, you know, well, combinations of temporal series with Bayesian updates. And I trying to put it all together and have better estimates. Also by removing in a sort of automated way the environmental influence, which can be a nightmare in existing building, because not only the temperature can be both positive or negative to the measurement you're making, but also the humidity in the masonry can be a key issue sometimes, and also the soil can be a key issue because it moves the building if the water table also moves. So there's many things complicating our life. I would say that there are many monuments monitored because they are unique, and it's easier to convince people in that respect. A very famous case study is the Tower of Pisa, which is being monitored for 500 years or so. But I believe many monuments in Portugal, I mean, we have several monuments monitored with dynamic identification or frequency measurements and crack opening and tilt meters, etc., temperature, humidity, etc. I think it's not extremely difficult, and the prices are going down. Unfortunately, one problem of a monitoring system is maintenance and processing of data, because this also has costs which are not so less relevant and which the client sometimes is difficult to pay. So structural health monitoring is a problem everywhere. Also, it's well known to be a problem in major new buildings or new facilities, bridges, you know, infrastructure, and major buildings where even, I mean, in a building with 100 or 500 million euro, people discuss inexpensive monitoring system and maintaining it. So it's not so easy to convince people, I believe, in any context. I think because the building is unique and people can understand, it's our function to make them understand that by monitoring, we are able to make a better job, which is keeping more the cultural value and the significance of the building and reducing the cost of the intervention. Also, something which is extremely important in my view is that we are working in a fraction of time. Most of the buildings I've been working have been around for 300 years, 400 years, okay, 500 years, or even 100 years. So what is 1 year in 200 years? And so, I mean, if the building is so unsafe that I send a letter or an email or a fax or whatever you want to say immediately, once you sit and you say it there, you prop the building or you remove the people or you take the things out because the building is unsafe, or it should not be hyper urgent, because if the building has been around for 200 years, it's very unusual that it's going to collapse tomorrow. Huh? I have, I mean, I know this is being too long, but I have an amazing story, which I would not like to give many details because of political issues. But I was called for something. It was on TV. And after a major intervention, which was mostly aesthetics, there was a collapse. And then they invited me. I mean, the collapse was quite lucky because 3 people fell. I mean, 2 on top of 1, but nobody got killed and the damage was none, almost. But the question is, if you have 5,000 of this typology, how many is going to collapse? Because 1, you know, it collapsed. And you already spent 100 million and you did nothing to stop this collapse, because, I mean, your 100 million was in painting, new frames, blah, blah, okay? So I went to this meeting with a lot of politicians and they asked me, what should you do? And I said, I don't know. And they told me, no, but we want to do it now. I said, I'm not going to do anything now because I don't know. And so I cannot do it. And then they said, okay, I mean, it took a lot of time to convince me that I could not do anything because, I mean, I saw one collapse. Great. I don't know why. I don't know the buildings. I don't know the condition. I know nothing. So how come I'm going to say do something? No? And then they said, okay, then we're going to say they are safe. I said, no, that I'm not going to say. And so we reached a compromise that they send me a letter, formal, and I send a letter formal, saying that according to my understanding, because of the age of this, very huge number of buildings and the typology that was similar, let's say in 50 years there was one collapse. In my understanding, the risk of a collapse in the near future was low. And my recommendation was to do nothing. If there would be a second collapse, which would be possible, my recommendation would be to prop everything immediately, which I cannot imagine the cost because it was ridiculous. And so, I mean, we have to be reasonable. In the end, we made a study for 2 years. It was a very complex problem. We were testing, we did lots of in situ testing, lots of calculations. Then we are still not happy. We did load proof tests for 1 year in the ones that we thought were, some were unsafe, we strengthened. Some were safe, it's okay. And some were in the middle, we test all in the middle, okay? Now, by doing this, in addition to not hassling the people using the buildings, I reduced the cost of the intervention 10 times. And so I think it was a good investment. So the cost, our initial budget was this value, and the actual cost of the works was 1/10 of this value. So I think it makes sense. So why do we need to act today unless we think it's unsafe, and then we have to act immediately? And so monitoring is justified, and I've been lucky to convince our clients to use monitoring extensively.
Thank you, Paulo. Now we are at the end of this talk. I only want to give you some information before finishing it. We are running a survey on which are provided on Facebook from EuroStruct side concerning the management of critical infrastructures during this pandemic situation. And those who are listening are invited to fill this survey. Also, from IAPSE, we have here the information about the symposium in Wrocław that was postponed to 7 and 9 of October this year, and with the task group meetings and welcome reception for participants on the 6th of October. And also from FIB, we have the information of the postponement of the conference in Shanghai to 22 to 24 of November 2020. Also, the abstract submission and the registration early bird is still open. And finally, with respect to EuroStruct, I want to inform you that there is now the registration for the online training course, which will be held online from 2 to 4 of September this year, and also about the EuroStruct 2021 conference from 29 to 31 of August next year on Padua, Italy. Finally, I would like to invite you to attend next week on the 25th of June at 3 p.m. Central European Summer Time, the talk with John Dunteman about forensic engineering and his experience. And then to finalize, I would like to acknowledge once again Professor Paulo Lorenzo, to be here with us, which was a very fruitful and very interesting talk. Also, I'd like to acknowledge Andreas for moderating this talk with me today. And for you, I wish you, depending on where you are, I wish you a good morning, good afternoon, or good night. So it is always a pleasure to have you here. And thank you again to everybody for one more EuroStruct talk and for being with us today. Thank you, Professor Lorenzo and Andreas. See you soon.
Thank you very much. Bye-bye.
Bye.